I need somebody help.
Elliptical orbit of Mercury. Let's chat briefly with this. First of all, I want to tell you right up front that the wording of the lab is confusing. So that's the reason I try to spend a lot of time going over it with you to try to make sure you understand exactly what's going on. So please follow along, as this is super critical for you completing the lab. The objective: students are going to plot data and calculate the eccentricity of Mercury's orbit in order to determine if Mercury has an elliptical orbit. It does in fact have an elliptical orbit, but you're going to more or less not discover, but calculate its orbit. Now, easy way to think about this is Kepler, right? This is all about Kepler. This is how he figured out Kepler's laws of planetary motion. He used data like this. So that's one of the things I really think is interesting about the lab. I took this from a college astronomy book, and it's way, way, way more difficult in that book, and I kind of watered it down a little bit in a good way. Let's talk about the materials you need: a millimeter ruler, a protractor, a pencil, and a calculator. Your protractor has a millimeter ruler on it, so that's at the very bottom. This has been blowing people's minds all day long, which I'm not real sure why. The big numbers on there are centimeters, and the small dashes are millimeters. That's blowing people's minds. So when you see 1 on there, that is 10 millimeters. Are you aware of that? So, planetary orbits, I'm reading right here, were discovered to be elliptical by Johannes Kepler in 1609, using the most accurate data then available on the angular positions of the planets. Remember, he used Brahe's big what? What did he use? Brahe's big
telescope.
Was it telescope? It was records, but Brahe took the data from the Big J telescope. You don't remember the Big J?
Yeah.
So I don't know if that's what it's called. That's what I call it. So if you see that on the test, be aware. It could happen. So Brahe took data for 20 years of planetary motions, and what was he doing? He's calculating, okay, today is August the 18th, and it is roughly 2 o'clock. I don't know, my watch broke, so it's 2:25. I see the planet Mars up here today. So this is the way he collected data, right? Now, using this data, Kepler concluded that the path of each planet around the sun is an ellipse with the sun at one focus. He took data and plotted it just the way you're going to be plotting it today, and came up with laws of planetary motion. It's amazing. The most amazing part about it is that you're going to be able to do the exact same thing. It's 400 years later. Now, part down here, you might want to star this. Something, circle it, I don't know, it's very important. These are the different parts of an ellipse. And I scribbled up mine pretty good, and it's pretty ugly. So, I'm going to point out some things I want you to pay attention to. The line going through the middle of the widest part of the ellipse is called the major axis. So from this side all the way over to this side is the major axis. You see how I did it right there? I drew an arrow that says major axis. Okay? You're going to bisect that line. In this case, they do it in the middle. On the lab, you're going to go perpendicular through the star. Okay? Are you with me? So you're going to find the widest path, then you're going to go perpendicular through the star. But that's going to create, this is what's called the minor axis, right? Major's bigger than the minor, that makes sense, yes. And then you're going to have two different ones. You're going to have a semi-major and a semi-minor. Is that blowing your mind? If you look at C, down here, not C, look at A, sorry, that's a lot. Look up at A, above the diagram on your paper. A above the diagram is the semi-major axis. B is the semi-minor, because it's only half, right? You know what semi means. Questions? That blowing your mind? All right, let's move on. We'll come back to that. That's the very last part of the lab. Flip your paper over. Now, I am a self-proclaimed genius, as I'm sure you're aware. It is self-proclaimed. But what really makes me genius with this lab is this ability. Watch, watch, watch. Now, you're thinking, you ripped a piece of paper apart, right? Yeah, but I ripped a piece of paper apart and I copied it in such a clever way. It's so clever. Because here's all the procedures, here's all the data, and this is where you're plotting it. Isn't that so clever? Oh my God, I wish everybody would just applaud or something. Thank you. Thank you. I appreciate it. And do it for the kiddos. All right. So this is where you're plotting all of your data. So here are your procedures, and here are your data points. Now I'm going to help you, but let's read through the procedures first. Procedures. Figure 19.2 gives Earth's orbits with the dates marked. All right, so here's 19.2. Have you already ripped your paper in half? Not in half, but separated, you should. You're going to start using the data immediately. It says, because of the small eccentricity of Earth's orbit, it appears as a circle with the sun at one focus, right? This actually is, you know, pretty accurate to the eccentricity of Earth's orbit, which is almost a circle, right? It's almost zero. So, it says, plot each of the maximum elongation values given in Table 1 as follows. So, let's look at the first one. Now, what is the maximum elongation point? Look at this date right here. You see it, 1967, February 16th. 18 degrees east. On this day and this year, Mercury was seen from Earth looking eastward, right? At, you know, roughly 18 degrees. Somewhere along that line. Are you with me? Now the distance is kind of irrelevant at this point because we're really not trying to calculate distance. We're trying to calculate the shape. So let's look at how you're going to plot this. This is going to be the most confusing part of the lab. East and west are backwards than you normally think of them, right? Most people, if you think of a compass rose on your paper, go north up, south down, west left, right, and right east. Are you with me? That's not the way this lab works, and the reason is because the Earth is rotating. So that's really the reason it's backwards. What you're thinking backwards. So I'm not trying to confuse you. I'm just trying to point out that that will cause you to mess up the lab big time. Now there's a simple trick to this. Anybody know Max Rafferty? Yes. Who doesn't? Okay. There's a student I had last year, and he came up with this really good theory. And I gave him credit for it because I thought it was really clever. I never really had a problem tracking it another way, but anyway. He said, if you turn the paper so the date's at the bottom of your desk, right? When I say turn the paper, you need to physically be turning the paper to where the date you're tracking is at the bottom of your desk. Are you with me? If you do that, the protractor always faces left for east. I'd write that down. It always faces left for east, and it faces right for the west. Okay? Write that on your paper. You should write that here. I mean, you can write it wherever. I don't really care. This is to help you. This is the easiest way to do the lab. Now, I've always just done it kind of with the paper in one position, just kind of went around the side, but it does make it easier if you do that. Now, let's look at the first one. You see how this looks? Look at this. This is going to look a little more like your finished product. Now, this is going to be one of those labs where you're going to be like, I hate this class, right? Maybe you say that all the time, but by the end of it, though, you're going to be like, that is a pretty cool lab. Because it really makes sense. It really helps you to understand how Kepler figured out this stuff using Brahe's J telescope data. All right, you ready? Let's look at the first one. First data point is February the 16th at 18 degrees east. Now, you're going to do all these data points. The years are irrelevant. It doesn't matter, okay? So, February the 16th, 18 degrees east. All right, pay attention. You ready? Ready? Yeah, did y'all see that coming? Anybody use the Promethean projector? Yeah. Let's hoping I was the first. Who's not seen this before? Oh, yay, a couple people. Yay. Okay. Now, you have a protractor, right? Why are there two of them? Okay. Now, you have a protractor. you're going to zero the protractor on February the 16th. You know what I'm talking about with zeroing your protractor?
Yep.
Pay attention, folks. It's right here where the little hole is. You're going to draw a little dot where your date is, and that's where your zero needs to be. You with me? This is going, this data point's going east, so you tell me which way should the protractor be facing?
Left.
Left is correct. Now when I say the protractor is facing, I mean the rounded part, okay? Are you with me? This is facing east. The rounded part is east. Now pay attention. Are you paying attention? Kitty, you paying attention? Okay, excellent. Now, I'm going to, hang on, sorry. I want to zero the sun. I'm zero here. Everybody looking? I'm zero here. I'm zero on the sun, right? Because this line here is on the sun. Are you with me? And it's zero. It's facing the east direction. That's the reason it's going that way. Now I'm going to plot my data point. 18 degrees. This has been a big point of confusion for some people, right? They're like, oh, that's not 18, that's 162. I'm kind of scared if you don't really know how protractor works, but I'll review it for you anyway, because if you're starting from this side, right, you use the lower numbers, right, 0 up, but the other numbers are if you start at the other side and go all the way over, right? So it goes either way. So this is 18. 10, 15, 16, 17, 18. You're going to make a little mark right there. Make a little mark right there. Do it right now. Do it. Do it. Do it. Do it. Did it? You need to have your protractor lined up, just like mine. Turn your paper down. Right. That's good. Now have your protractor facing the exact same way. I put the dot on there when I copied it. Wasn't that nice of me? Do you see that?
Yeah.
For February 16th? See, look, there's the dot. That's 0. That was on 0 for the sun. They can go 18 with a little mark right there. That's what the data says. Look. 18 degrees east. Who's got the mark? Beautiful. Now you can either use ruler or the straight edge of your protractor, and you're going to draw a line from the date, intersecting the point here, and going all the way across the other side of the circle. Okay? Just like I did in the red. You see that?
Is it supposed to reach September 20th?
It's going to basically be at September the 20th or September the 21st on the other side. Yes. If you do it correctly, it should be somewhere around that. That looks great right there. That's good. Questions? Let's do the second one. Second one is the 31st of March, 28 degrees west. So turn your paper where it's at the bottom. That's pretty close. So I've moved my paper around too, do you see? I tried to rotate my paper around. And I've got March 31st just right here. It's close enough. I'm not even going to mess with it anymore. Actually, I mess with it a little bit more. Why not? Ah. That should be good. That's close enough. Now I'm going March 31st. What's the 28 degrees west? So if I have the paper facing down, which I do, which way's west?
Right.
Exactly. Right. So I'm going to move it. Remember, 0 it. March 31st. That's where the circle is in your protractor. The 0 right there on the date. Put your little mark where the date is, because you're going to need that point in a minute. And now I'm going to dump this, a very important step. You have to re-zero on the sun over here. See? I re-zeroed here on the sun. Okay? So now I'm on my date. I'm on my sun. Now I can go to 28 degrees. There's 30, right? And then 28 be roughly right here, and I'll make the mark. And it's going to shoot across there. We'll hit somewhere close to August 1st or something like that. When you finish, plotting the data. Guys, here's the next step. Look, 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 look. I know you're excited about drawing lines. The next step is right here in your procedures. I assume you can read over it. I'll be happy to help you once we get to that stage. Okay? And we'll come around and make sure that you're getting started on the right foot. The biggest trick is the east-west trick, okay? Turn the paper where the date's at the bottom of the page for you, and then don't forget the little tricks, right? Left is east, right is west.